Hi, my name is Muhammad Abdurrahman, and today I'm presenting a work that we have been doing through the semester about assurance monitor design pattern. This was a collaboration from lots of people. Manny is from Caltech, Juan Gonzalez is from ECE here at Rice, Adam Duresh, Yao Jiang, Korki, Krishnan, Riichi is from the Computer Science Department. So I will start the talk by explaining some basic concepts. Then I will go through what's assurance monitor design pattern. So first, what's a design pattern? A design pattern is a reusable solution to a commonly occurring problem or product. So think of if you're building a car. If you're building a car that's composed of multiple components like tires, engine, windows, and things like that, and you're trying to manufacture a car or collect a car or design a car, so you need all of these components designed to help you doing that. The same idea if you're building a plane, an aeroplane, it has different components like wings, maybe it has an elevator or like different components as you can see. So you need this kind of design to help you design your plane. Same idea if you're building, if you're designing a building, mosque, church, synagogue, anything of this kind. In computer science, we have what's called a software design pattern. As you can see here, this is a common architecture for different kinds of design patterns. I will select one of them just to illustrate the idea of what's a design pattern in computer science, which is a singleton pattern. A singleton pattern looks like that. So it's basically what's basically doing is just preventing the programmer to have multiple instances of the same class within the same runtime session. Think, for example, of a date class. If you use Java, and trying to get the current time or date while you're programming. So you don't want like two different instances or more of the date clause to prevent any kind of inconsistency. The same if you're doing a database connection and you're working with the database to insert data, select data. You don't want multiple connections within the same runtime session to prevent inconsistencies. So design patterns have been used across several domains. One of the most interesting ones proposed by Fernandez and Pan in 2001. This is one of the most cited papers. They present different patterns. I choose some of them. The authorization pattern that we can see in multiple web-based systems and desktop applications is basically having class for subjects, class for objects, and access types. So you can have different access types or privileges that you can give to subjects to access certain objects. A higher level than that is the role-based access control pattern. As you can see, it's the authorization pattern is a subset of it. So here you have different roles for users. So you might, for a web-based systems, you have administration, you have users. Of course, they have different kind of access types of privileges. So you need to model this in a design pattern to help you developing your web-based system. Another level is the multi-level security pattern. Here you have another kind of pattern. You have different levels of data and different categories of data, multiple processes, and even a hierarchy of users within the same role. Think of it like if you're using Canvas. For a certain course, you have an instructor, you have TAs, and you have students. So they have different access levels of data and menus. Another example of using design patterns across domain is information visualization. If you have like information that you want to present visually to you, this again it was presented in 2006, one of the most cited papers. I choose 3 patterns to present here. One of them is the data column pattern. This helps you designing a table visually instead of like writing queries, which could be a basis of something we know in database called a query by example. And instead of letting the user writing the query himself, he can use a design like that to build up the query and the conditions. Another pattern that was presented is the relational graph pattern. This one is used to select data from a table or something and present it visually in a graph using edges and nodes. This can be a basis to something like modeling friendships on social media, maybe something like a supervisor-student relationship, something like that. One more pattern is the camera pattern, to have a camera visually to you, like virtual to you, to model the different transformations and views of the camera. That can be used to play with the scene or like used in a game or something like that. Design patterns have been applied to different domains. I just chose a couple of them. It was applied to programming languages, distributed processing systems, and lots of things. As you can see, it's clear why we need a design pattern. It saves time. It gives you like a procedure that you need to follow in order to finish your design. I will switch now to what's the assurance monitor. Then I will continue about the assurance monitor design pattern together. So what's an assurance monitor? The assurance monitor is a kind of a constraint-based system. When you have certain constraints in your system that you are trying to avoid violating while going through the system. For example, think of a drone that's flying over a region that has a military area or something, and you are trying to avoid it. And you have limited resources like energy, for example, the energy of the drone. And you're trying to avoid constraints like not to fly higher than a certain level, or not to reach a certain level of battery of the drone or something, and still avoid the no-fly zone of the military region. Of course, we didn't have a drone to fly over a military region. That's forbidden to do here. But I have a video here to show you the concept I'm talking about. This is a drone that was flying over the south coast. And as you can see from the text above, it's struggling, staying in position because it's flying higher than the constraint that was set in the system. And also it's affected by the wind because it was a little bit windy in this day. And the guys controlling the drone is trying to get it down or like deal with it to avoid being crashed. They didn't do that, of course, as you can see from the title here. So after a while, as you can see, the drone crashed, and in a few seconds here, you can see the dogs here. Good that it's kind of a bird or something, and they are trying to approach it. So I hope this illustrates what I mean by assurance monitor. So after that, what we have been doing is combining these two together, applying design patterns to assurance monitoring. And through the next slides, I will be presenting what's the design pattern we proposed, and hopefully I have time to present an example for that after that. So this is the design pattern we mentioned in the paper to help in assurance monitoring. So we have different type of agents. Why it's agents here? Because we have data streams. As I showed you, the drone is moving, so you need data streams going on the whole time. So as you can see, you have here sources, which we call the data source agent. The blue one is the prediction agent. Fuse measurement agent is in green, and check validation in red. And the control is just the controller that we use, for example, for the drone to control it. I will go through each one of the agents, explain what it does briefly. So the data source agent, you can think of it as something that data coming from a sensor. Like in the drone, it's a sensor that measures energy, maybe a drone that can measure the weather around it, something like that. So it's a stream of data coming from the sensor all the time. The fusion agent, or in the picture before, it's a fuse measurement agent, is taking a probability distribution of trajectory. Why? It's a probability distribution. So think of the drone taking pictures while it's moving. and assume that you have offline images of the region that it's flying above. And you're trying to approximate the location of the drone. So you're comparing the image that drone is taking with the images in the database, and you're trying to approximate the location of it based on that. So through time, that's why you have a distribution, because at every time unit, you have an estimation if the probability of the drone being in this location or not. That's why I have a probability distribution. And it's taking the measurement at time t from the sensors we have, and it update the probability based on that. So it's fusing information from multiple sources and giving you an updated probability distribution. For the prediction agent, it's similar to the fusion agent, as you can see, but it's triggered by a controller. So the controller should ask for the prediction agent to work instead of having like measurement at a certain time. The most important one here, it's a check violation, which is related to the assurance monitor that we are talking about. We are trying to avoid breaking or violating a constraint. So it's taking the probability distribution again. It has the resource availability. Think of it like as I said, the energy of the drone, for example. And it takes the constraints, avoiding the no-fly zone, not flying over a certain height, for example. And it outputs two kind of things. So a data request, in case it cannot predict the future, the data it has cannot like help predicting the future. So it requests more data from the sensors we have. And feedback to controller, either two things. The first thing, it's kind of unsafe now to keep flying because we're breaking the constraints. So we need to make a corrective action. For example, in the video I shown that it should lower the height of the drone, for example, or something else to put like as a feedback to controller that it should continue working and we are safe. We have enough energy and we are fine not breaking any constraints to keep moving. So this is about the check violation agent. For this kind of work, the assurance monitor, it's hard to evaluate it using quantitative measures that different systems, like in databases or things like that, or bioinformatics. So in this kind of systems, the way we evaluate it is to put it in practice. So that's, in the next slide, I will show you, I will continue using the drone navigation example and show you how we apply the design pattern in this case. It's kind of a bigger design pattern here. We have three data agents, as you can see, the IMU, camera, and sensor. Two fusion agents, the capsule and GPS. Just to mention what's capsule, I think it was covered in a previous COM600. And it was developed by a team in South Korea and a team here. I think Chen was among the team, and Anshu and Krishna. So what capsule is doing is comparing the image you are taking at runtime with some offline images and trying to get an approximation of your location based on a distance measure, basically based on locality sensitive hashing. So the drone, again, here is, we simulate the drone flying over a region where we have a no-fly zone, like I said, the military region or something like that. And we are trying, while the drone is moving, we're trying to approximate the location while it's moving. So we have three things, three data agents here. A continuous stream of acceleration measurements based on the accelerometers and gyroscopes of the device. And also we have the data stream coming from capsule, which is an approximation of the location based on comparison of the images. And what the check violation here is doing, based on the energy we have, and the drone, if the drone cannot, if the system cannot approximate the location of the drone accurately, it asks for more data, which we can get from the GPS, which of course is more costly. So it checks first if we have resources available to do that. So also, that's all for the drone navigation. Also, we applied that to data integration, which is used as a basis for recommender systems, and also to timestamp sensors, and it could be extended to different kinds of applications. To sum up, first the design pattern, as I explained, can save time, improve the communication through basic concept that we agree on at design time. As a proof of concept for the design pattern proposed, I showed the drone navigation, and in the paper we submitted, we had examples for data integration as well and timestamp sensors. We started, and I think we almost finished, done with the library for that has like the different agents written like as functions in Python, and it serves like different kind of systems, distributed systems and multi-agents. And I think we can release that after the conference, which will be in New Zealand in June. For that, I conclude my talk, and you're welcome to ask any questions.
Putting together several key components, while these key components are already contributions of others. And could you maybe comment on why your design pattern is so significant that we should adapt it for other systems, and how applicable it is for other systems?
For other systems. Okay. So I think I have time for that. I prepared like extra slides for that. This, for example, is the same design pattern, but with just one Fusion agent, as you can see. This was applied to data integration, where we have multiple sources of data, like a database, Excel, XML sheets, and things like that. So, and the Fusion agent is taking data from the multiple sources and integrate them and cluster them and give some estimates of the values inside them. So think of it if it's applied to something like a movie service, like Netflix or something like that, and you're trying to predict if the user or whoever is watching a movie is going to finish it or not. So you can apply the same pattern, especially the prediction pattern, using the probability distribution over the different kinds of or different types of movies, and based on the history of user profiles to predict if the user can finish the movie or not. This is an example of how to apply such a design pattern in a different application. I hope I answered your question.
How do you represent the different probability distributions?
Okay, so the question is how you present the different probability distributions.
Represent.
Represent them.
Yeah.
So you can represent them like using any kind of equations. So it's based on readings from different sensors. So you can think of something like a laptop, and you're trying to estimate when your battery is dying. So you get like different readings from the sensors in your laptop, and you present them like different kinds of equations. So I don't have like a specific representation. So it depends somehow on the applications you're applying the design pattern on.
Okay, but like in the two-dimensional space, when you're looking at a position, like a latitude and longitude, it's just like a...
So just it could be like a function representing like a line or some sort of a curve, something like that.
Can this design give the real-time feedback to the system? Or not?
I'm sorry, what kind of real-time feedback? Like,
For example, like for the drone project, if you like, so you take a whole chunk of data for a long period of time and give the prediction for a long period of time, or give like, you can predict the current point, which direction the drone is going.
yeah.
The second
So
one?
it gives you. So while the drone is moving and you have these readings, you can predict if the drone is getting near the no-fly zone or not. So it can say that you're close to the no-fly zone in the real time.
And then on the example you showed on slide 10, I was confused since you now have two check violation stages, whilst your general design pattern is one. So in this case, it seems to not match directly to the...
Okay, got your point. So the design pattern I presented at the beginning was just one Fusion agent. That shows the scalability of the design pattern. So in this example, that shows that you have two Fusion agents because you have a GPS and a capsule system. That's why you have... So it's extended to have like multiple Fusion agents and multiple check violation agents as well.
I have a question on designing design patterns overall, how do you evaluate a design pattern? Like if I were presented 2 design patterns for doing assurance, how do I know which design pattern is better? Is there a way to compare and understand what's good about a pattern or what's bad about a pattern?
So the question was, if you have multiple design patterns for a specific system, how you say this one is better than this one? To be honest, I don't know the exact answer, but I think that comes into my mind is maybe you have some metrics like scalability, for example. If it could be scaled to different kind of systems or not. Like this one. The original design was 1 fusion agent, right? And it scaled to 2 fusion agents and 2 check violation agents. This is one of the metrics that you can use to judge in this case.
So kind of going off of what Sunny's question earlier, so like for example in robotics, this kind of feedback loop is like very common. Like back in the 70s, people were doing linear quadratic Gaussian control and things like that, which is just you have some sensor fusion and you have some control feedback and prediction process. So can you comment on, you were talking about things like recommender systems and things like that. Are there examples of this design pattern, maybe not described in your terms, but from those fields as well?
Up to my knowledge, I didn't read like papers applying design patterns with this sense into robotics, for example, but I would love to go through this with you, with your help, for sure.
So we should. So we're going to go ahead and wrap up since we have Dimitri planning to speak today too.
Thank
Can
you.
we thank Tom